All right, so that's the very simplest learning method. Just memorize everything. Rote memorization. Some people call this case-based learning because you're remembering all these cases that you saw before. Like I'm not a lawyer, but people tell me law works a little bit this way, that if you have some legal question, there's all this big tradition in American law about precedent, and you look for a case that's very similar to the one you're confronting now and see how they decided it. And some people call this case-based reasoning. Okay, so that's that. So let's move on to something sexier. So neural nets. Everybody loves the brain. This has the word neuron in it, therefore it must be cool. So what's a neural net? It's a bunch of neurons stuck together. So in a network. Okay, so.
I see the word perceptron on there, so I'm sold.
Oh, perceptron, yeah. Okay, so k-nearest neighbor is a fun learning method, but oftentimes people have data sets that are just too huge. So figuring out the nearest neighbors is just impossible. And there are two things you can do. One is you can throw out most of your training data and keep some small, hopefully representative sample of it and just do k-nearest neighbor over that. And the other is use a different learning method. So a neural net is a kind of learner that's specialized for numeric data. And let me draw a picture. People often draw pictures when they're talking about neural nets. Let's see. I can never remember. We're going to have a whole bunch of neurons. You guys know what neurons look like? Yeah, exactly. Actually, a real neuron it's got a circle, but then one side of it's got all these little squiggly things. And then the other side has this long thing that then has some little squiggles at the end. Yeah. A giant squid axon. Yeah. Well, they can be teeny tiny. And this is the cell body, and this is called an axon. And then there's some other little neuron over here who's going to get tickled by this guy. And his axon's going to go off somewhere. It's just totally nuts. The neurons don't actually touch each other. There's a little bit of water in between. And so what happens is this guy gets tickled by whoever he's next to, and all of a sudden he sneezes. He goes, achoo, and sends an electrical pulse down this line here. And then when he gets here, the chew, it's just like when you sneeze. You know, all that spit comes out of somebody's mouth. So there are all these little neurotransmitters that go and go into this little gap here and diffuse across, and then they tickle the dendrites of the next guy. So everyone likes to say the brain is electrical, but it's actually electrochemical because the electrical pulse has to go by chemicals across this little gap to the next guy to tickle him. It's just unbelievable how this. And in fact, the way the electrical signal travels down the axon is by the opening and closing of these little pores in the wall, in the cell wall, that let charged ions in and out. So the charge is changing. So you have this traveling charge. So it's electrical. It's mind-boggling stuff. Anyway, so basically it's a dot with a line. So here we got dots. So now it's time for some lines. There we go. Lines. Okay, so that's a neural net. Dots and lines. This is going to be called the input. And let's call that the output. And now, just like people, some neurons sneeze more than others. So given how excited these neurons get, what's going to happen is we're going to the new example that we present to the learner, we're gonna set the value of these neurons here. So if we're learning like, oh, engine displacement of 1.6 liters, we put like 1.6 here, and if it's a 4-door, we put a 4 there, and if it's a 6-speed transmission, we put a 6 there, and if it's got a panoramic sunroof, I assume we put a 1 here rather than a 0. But I don't know, maybe we put a 2 if it's got a panoramic sunroof. If it's got a normal sunroof, we just put a 1. So we assign numbers here. And now the question is, how much is this guy going to sneeze out here? What's the strength of association between these two neurons? And that's set by a weight. So for every input I, there's a weight, Wij, that says how strongly input I is connected to output J. Now, if we only have a single output, we just have these weights I. So we'd have something like the output is equal to the sum over all the inputs of the weight times, I don't know, x, we'll call the input x, xi. Is this looking suspiciously familiar to anybody? This is just a linear equation, a weighted sum of x's. So all neural nets are just a fancy way of doing regression. And a basic neural net just does linear regression. So I hate to break it to you, but all this sexiness about neural nets, a basic neural net is just doing linear regression. You're setting these coefficients, which here I've called theta, on. Now, oftentimes people use fancy features of the input. They might not use the input features directly. You might have some feature. Is this looking kind of familiar too? Maybe what you did exactly last Wednesday for approximating a value function? Maybe it's exactly the same thing. You're representing some linear function in terms of features, and we're getting some approximate output. So that's the output of our predictor. In supervised learning, there are really two things you can be doing. You can be doing classification or regression. Classification means you're looking for a yes-no answer. Regression means you're looking for some kind of number to come out. And like any good scientist, the first thing we do is simplify the problem. And we'll just make classification a special case of regression. We'll say, okay, if the output we learn is closer to 1 than it is to 0, then it's yes. And if it's below 0.5, then it's going to be no. So for example, I'm going to give you pictures of handwritten digits, and you're going to tell me what digit it is. The way you're going to do that is by making 10 different classifiers. Each one is trying to say, is this a 5? Is this a 7? Is this a 6? And we'll see which one. We're supposed to have 10 yes-no answers, and hopefully only one will be saying yes. But since classification is just done by regression, you're just going to see which one has the highest output, and that one wins, and that's the answer you're going to return. And you'll train your classifier by, if it is a 7, the output is supposed to be 1. And if it's not a 7, the output is supposed to be 0. You silly classifier. So this is just linear regression. And an amazing amount of machine learning, this field that do you know how much money companies spend on machine learning? Like Amazon to do product recommendations, or Netflix to do movie recommendations, or Walmart to figure out what people want to buy next. Did you guys see the article in the paper that Target can predict whether somebody is pregnant by looking at what they buy? And there was a story about some guy whose daughter got these Target coupons in the mail for stuff for like expectant mothers, and he was affronted, and he called up the store manager and was like, how dare you send my teenage daughter this stuff for expectant mothers? What are you trying to push? And the store manager called him back a few days later to apologize and say, I'm so sorry you received those mailings. And the father said, well, actually, I've had a talk with my daughter. And this like freaks people out a little bit, right? Like, you know, they know more about what's happening in my family than I do. It's a little freaky, the kinds of stuff they can predict on the basis of consumer behavior. So what they do now is they're always sure to put lots of other randomly selected coupons in along with the ones for expectant parents so that you're not offended and you don't get creeped out. Anyway, companies are really into machine learning these days, and especially for large-scale machine learning, it all boils down to linear regression. So I don't know about you, when I was an undergrad, I was like, linear regression, what a stupid technique. How many things in the world are lines, right? Like nothing. So don't talk to me about linear regression. Boring. And what happened is I had forgotten about these f functions here, these features, right? So for me, it's like distance from Kingsbury. That's what's important. But that ain't no line. That's a cone, right? Distance from goes the inverse cone, I guess, goes out radially, right? So if you want to learn something about how wonderful a state is or how wonderful a particular housing option is for a computer science major, it's not linear in latitude and longitude. No. It's linear in distance from Kingsbury, right? So it's just a question of what features you apply. If you apply the what's the distance from Kingsbury feature to the housing option, you'll get back the distance from Kingsbury, and then we can assign a high weight to that. So we're learning the output, how wonderful it is, based on how far it is from Kingsbury. It's all about the features. It's not so much about what learner you use. Linear regression is actually a fabulous technique.